Hello. First of all, thank the organizers for the invitation and for the support. It's really great pleasure to be in this nice place. Today I'm going to present the results of our recent paper which we published in the archive in the number. It is micropaper. Well, to give you an introduction, to show the introduction to this problem, I'm going to remind you about this couple of beautiful papers by DSTV, published in 1983 and 1985. And these two papers laid the ground for many excellent detecting experiments which are running or which are completed now. So, such experiments as ADMX, ORGAN, Russian wall, and many other experiments. I'm not going to mention all of them. So what we consider in our paper, we actually consider the scalar field that matter. So the scalar field phi interacting with the magnetic field, if you know what I mean. This we are going to consider just this type of interaction in our paper, and we assume that scalar field phi is the dark matter, phi. So the main questions, we are going to address, which we address in our paper, as the following: are the Axion search experiments sensitive to the scalar-photon happening of G, phi, and gamma? And if they are, so how to maximize the sensitivity of this experiment to the scalar field at night? Or maybe we can actually make something better, and if we take the scalar field at matter seriously, maybe we can construct some new experiments and develop some special field dedicated to research of this particular type of dark matter. Okay, this is the reason I'm going to give you a bit of theory because our work is not theoretical. So this is the region, the stable region with the scalar field interacting with the electromagnetic field. Well, and we assume that the scalar field is just a gray wave. Phi 0 is the amplitude of the scalar field. So these are the Maxwell equations. Maxwell equations which include interaction terms of the scalar field that matter with the electric and magnetic field. Now the predicted approach, predicted tree, which works for axions, and we can do the same for the scalar field. These interaction terms may be considered as the effective charge and current density of the Maxwell equations. And so, if you have a constant or dominant electric and magnetic fields, then the effective charge and current densities have this simple expression. It just means that electric fields, the ground electric and magnetic fields serve for the source, for the forces. Well, and now we see quite standard, quite simple exercise to solve for the Maxwell equations and find the photon signal in the scalar field to photon diversion. So this is the equation which we can get from the Maxwell equations, as called Maxwell equations. So this is the power of the photon signal. And this is the formula I would master, but you can compare this formula with the similar formula which was found by CTV in the case of Axions. So the main difference is the coupling constant. Here we have scalar coupling constant, here we have axion coupling constant. And the main difference comes here. So the roles of the electric and magnetic fields are swapped in this expression. So now I'm going to consider some consequences of this simple exercise. So I just switch over to the ground electric field and consider just the magnetic field because in experiment you prefer to use magnetic field. Yeah? So here we have this expression. Beta is the velocity of that matter particles. Here we have cross product beta and B0. So that means, well, and we have square. So it means that this signal is usually suppressed by the beta square, because beta square is 10 to the minus 6. And this is not actually good, but the other thing is this factor, sin theta squared. It means that experiments detecting scalar field that matter may have will be sensitive to the modulations of the signal, daily and annual modulations, if this field angle changes. But now, what about cast experiments? In cast experiments, you detect solar axions, right, which are produced in the sun. So they
no more. That's okay.
Okay, they have a high energy, keV range. So and beta, in the case of solar axions, is close to 1. And moreover, in cast experiment is detected located on the moving platform which tracks the sun. And so theta squared is basically 1. It's also very close to 1. So it means that for experiments like cast, they are equally sensitive to axion to the scalar fields. Well, that's why I think the we construct which will found by cast for the axion, and I simply make the same space for the scalar field that way. So this is the very simple but interesting consequence. Now about cavities, cavity experiment. So I'm considering let's consider any cavity with the magnetic field B0. So in the axion case, the signal power is given by this expression. It was found by CT in 1995. So and the important ingredient here is the form factor. Form factor C here. It describes the interaction of the ground magnetic field with cavity models. And here the form factor is B0 times E. E is the electric field of the cavity model. In the case of scalar field, like matter, the expression for the power of the signal is pretty much similar. So the same expression for the R. But the new thing is about form factor. In the form factor, we have the following pattern. B0 couples to B alpha, so magnetic field couples to magnetic field, and electric field couples to the electric field. Of course, if you have the electric field mechanics. So with this line, I separately consider cases. The two cases like the case has magnetic field and electric field. Maybe you are not using electric field in case, but I'm just theoretically consider this case. So and there is some numerical estimates, physical units in watts, or the signal which may be achieved in this case, in the case of the scalar magnet. Okay, now about cavities like in the ADMX experiment. Well, we calculated actually the form factor for the case of ADMX experiment cavity. And the way to use is that this form factor is actually very small. So, because in ADMX cavity is dedicated for the axion search. Well, and it's not very well suited for the scalar field at night. But the good thing is actually that this form factor is not vanishing. It makes this suppression, of course, but it's not zero. It's not zero. So this value may be small, but it's not zero. It means that we still can find constraints for the ADMX experiment on the scalar field at night. And so what we have done here, we did rescaling. So we just took the same results found by the ADMX experiment for the axions, and we rescaled these axes appropriately using this small value for the form factor. Because for axions, the form factor is 0.4, and for scalars, it becomes much smaller. All right. So now, there is a couple of ideas how we can improve this problem. How we can resolve this problem with a small factor. So the most naive is to use the electric field. If you have an cavity with electric field instead of magnetic field, the form factor may be large. It may be close to 1. But you know, in experiments, magnetic fields are preferred. So if you want to have a cavity with magnetic field, you need another geometry for the cavity, an topology. So the cavity, I think that the cavity of this shape, like ring shape, may be good for detecting scalar field at night. Because magnetic field is is oriented in this way. So these red lines are magnetic field. It means instead of vertical magnetic, instead of on the z-axis, you need magnetic field in the plane. So this magnetic field may be created by this solenoid of this shape. And then the form factor is again close to 1. Now, last but not least, of course, slide about another proposal of broadband detection, scalar field that matter with the capacitor. So this is some scheme. Well, here we have a capacitor, and capacitor is supposed to be charged with high voltage V0. So V0 is the ground static electric field of the capacitor. Now, the scalar field that might interact with this electric field, and it creates effective polarization. It's not physical, but effective polarization. And now, the effective polarization actually creates the physical electric field inside the capacitor. But this electric field is oscillating, it's not static anymore. That's why the signal would be oscillating voltage of the capacitor. And it's not resonant. So, in principle, this is a broadband experiment. So, that's why we can detect scalar field in large range of masses. So this is the estimate of sensitivity of experiment which we did, assuming some reasonable values for the voltage on the capacitor and the sensitivity of the detector. So we hope that, we expect the sensitivity of this experiment may be comparable or even better than the molecular spectroscopy experiment. Okay, this is my summary. So we calculated the power of the photon signal from the scalar-photon transformation in resonant cavities. Then we got new units of the scalar-photon carbon quantum just by repurposing the results of CAST and ADMX experiments. And so we did some proposals to maximize the sensitivity of these experiments. And finally, it's maybe very interesting technique, we propose a broadband experiment based on the capacitors. So that's it, thank you.
What determines the low frequency cutoff in the capacitor requirement in your previous slide?
Well, in this slide, this region of masses was basically selected by the sensitivity of the detector. So it depends on the sensitivity of the detector to the low frequencies and to high frequencies. So in principle, if you take another detector, so it's just sensitive to small frequencies, so it would be possible to shift to small and or to high frequencies. For the capacitor itself, I don't think it's a problem.
Yeah, it's a problem.
So we just put some particular detector with a given range. So in principle, we consider different detectors for amplifiers like this. So I need a high impedance amplifier for detectors with oscillation, very small oscillating.
What's about if you put ferroelectrics as materials in the capacitor?
Yes, the question. So in this capacitor, we can consider just vacuum here. You just vacuum, right? But in general, we can consider a capacitor with some medium inside, ferroelectric, ferromagnetic, or whatever medium. And in this case, ferroelectric. Talking about ferroelectric. Yeah. You can put the some medium inside this capacitor. But in this case, the interaction would be not just with the electric field, but with electrons. So such experiment can probe not just we consider just one coupling constant, G, phi, gamma, gamma. But then there would be sensitivity to other coupling constants. So whereas the scalar field interacts with electrons and maybe with baryons. So yeah, well, it makes sense, or it really makes sense to do this.
So also in this case, the time dependence is due to the angle between the beta of the field and the background field.
You mean dependence on the angle in
So this is the sine theta.
Yes,
That's
of course,
it.
yes.
So you either could just set a stationary detector and wait for the Earth to get you through the scalar field wind, or you could set on a turntable.
Yes. Well, both cases work well. So if this detector is stable, then just rotates around the little scalar fields. But of course, yes, you can modulate it artificially, so you cannot take the detector. Absolutely great question.
Yes, I have a question. It's a naive question. It's about ADMX and using cavities to get the signal. So I was wondering a little bit, for axions, I understand that you have a magnetic field and you're waiting for an axion to convert it to an electromagnetic force to get some photons out of this. But then if you're looking for a scalar, that I guess you don't have an electric field to sort of to enhance, I suppose, the cavity in the first place. I guess I'm just looking for some intuition for how exactly the beautiful photon signal in your cavities.
Cavities.
Yeah.
So it's a technical question for people who design these cavities. So in cavities, they usually put a small antenna inside the cavity and they read out the signal. The antenna has to be specific it should be special in order not to break the modes because it makes mixing across modes. But typically the antenna just reads out the it reads out the signals, the photon signal oscillating modes inside the cavity. Well, in this ADMX experiment, when we do system checks and we found these limits, we just assume the same cavity or the ADMX unit or with the same antenna. But if you want to consider another experiment like this, so I don't actually know, maybe the other type of antenna would be more suitable here in this experiment. But from the roughly naively, I think that zero antenna when we still work in this case.
Can we use the loop antenna to the field?
Again?
We use the loop antenna to the field, oscillating the field inside the cavity. Yeah.
Usually, well, antenna is detect electric field.
Yeah, exactly.
So for magnetic fields, you mean cases like
We didn't be looking
wow,
around.
that's
The loop antenna has a loop.
well, it's a technical question for people who design antennas. I don't know.
Is there a question?
Hi. So you're proposing an experiment where you maximize your sensitivity to scalar dark matter using a different magnetic field geometry. Can you just use like the same Solomon and use a T mode, the T010 mode?
Here we propose to measure TM mode. With TE mode, it's still interesting to consider such modes. But for in the experiments like this, TE modes will be very small. In this particular case, it will be very small. But they may be interesting for another case. TE modes, it's still interesting to measure this mode. I can show you why. Look, this is the expression for the form factor. And the form factor has this little factor, exponential. Explain P is the momentum of the incoming scalar particle. So usually you assume that the locality is small and the wavelength is large and you ignore the spectrum. But you don't need actually to do this. And you consider still you can expand this exponent and consider the first linear term, which depends on the momentum of the particle. And then, yes, you can measure such terms in this case. And TE modes can be particularly useful for measuring modes which depend on the momentum of the kind of scalar mathematical particles.
So I think we can go to the next part.